Hi, welcome back to Math with Patrick. It's May 1st, and we're solving problem number 121 from this Daily Epsilon calendar. And we need to show why this sum right here, plus a little bit more, is just equal to the number 1 today. And at first glance, this problem seems really hard to me. Let's just get like an intuitive, base understanding of what this notation means and how we might even be trying to figure out how this is the number 1 today. We have some more summation notation. We've encountered this in the past, where basically we just plug in n equals 1 right here, and then whatever value I get, I'm going to add it to the next value when n equals 2. So I'll plug in a 2 here and here. And then I will add it to the next number when n is equal to 3, and so on up until we get to this top number, which is 99. So that's a lot of terms. That's 99 different addends, or things being added together. And then finally, when we get to the 99th addend, we're going to add one more. And then that's going to be equal to 1. So when n is 1, I see a 1 over 1 plus 1 factorial. So that's just 2 factorial. Then I'll add 2 over 2 plus 1 factorial, or just 3 factorial. And then 3 over 4 factorial. And so essentially, it's just going to follow this pattern of incrementing up by 1 all the way until we reach the 99th term in this sum. That's when n is 99. So we'll have 99 over 100 factorial. And then that's this y right here. And so if I add on a 1 over 101 factorial, this sum right here with 100 terms apparently is equal to the number 1, because that's today's date. If we figure out what those factorials are, we can see that it's like 1/2, and then 2 sixths, 3 24ths, because factorials are just multiplying all of the natural numbers at and below your current number. So like 4 factorial is just 4 times 3 times 2 times 1. And these factorial numbers grow very quickly. And so even by the 4th term in this sequence, I'm getting numbers that are quite small. 4 over 120 is very close to 0. And apparently when I add up all these things, I get a 1. I'm not quite sure yet why it equals exactly 1. And also, this number right here is so small. It's 1 divided by 101 times 100 times 99 times 98, all the way down to 1. It is astronomically low, so close to 0. And I think it's crazy that this whole sum is equal to 1. We're going to have to pull out some bigger tools today to actually prove why this is the number 1 on the screen right now. So let's imagine that we have this box, or I guess it's a square, because box kind of implies 3 dimensions. So it's a square, and let's just say it's 1 by 1. So the area of this square is 1. And let's see what happens when I keep trying to fill it with these fractions up above. The first one is just 1/2, and so I'll color code that here, where I'll just split this box in half, and then I'll fill it in with the number 1/2. No big deal. The next one's a little bit weird. 2 over 3 factorial. That was 2 over 6 that I did earlier. And so if I split this box into 6 pieces and I shade in 2, that's going to be the same thing as like adding 2 over 3 factorial. So I think let me use a different color. I'll use this red. And then if I split this box into 6 pieces, I guess it could kind of look like this, where I've 1, 2, 3, 4, 5, 6. And I'll take 2 of the parts that I haven't shaded yet and shade them in, and that will kind of represent me adding in 2 sixths. So here's the 1/2 that I erased, and then here are the 2 sixths that I'm adding to this box now. The next fraction is 3 over 4 factorial. That is 3 24ths. And so if I split this box into 24 pieces and shade in 3, then I'll add in 3 24ths. And I'm noticing like this interesting geometry pattern going on here where I don't really need to do the whole box as long as I just kind of slice it just right. Okay, so you could imagine if I had these 3 blue lines over here as well, I think we would have 12 pieces, right? There's 4, 8, 12 on the right side, so there's 24 total. Then I will shade in 3 of them, and that will be right here. And then so that's that amount right there. Maybe you're kind of seeing the same pattern as me right now, where I basically am slicing the remainder of the box and shading in almost all of it. So let's see, let's do orange. I feel like that'll show better. This like nice like orangey yellow. Okay, 5 factorial. I need to split this box into 120 pieces because that's what 5 times 4 times 3 times 2 times 1 is. But I know I could also just take a 24th and split that into 5 bits because 24 times 5 is 120. And so I'm pretty confident that each of these small pieces like are a 120th of the whole box, except that, my lines were a little bit out of place. So let me see if I can make them a bit more even. But I'm going to shade 4 of these. And as you can see, I'm not shading the whole box. I'm shading almost the whole box. The next one, I will split this into even more smaller bits and color in all but one of them. So you can imagine if I keep doing this process infinitely, I'm eventually going to reach the number 1. But if I do it finitely, like I'm only doing this process 99 times, I'm not actually shading in the whole box. I'm shading almost the whole box. And so I'm hoping that this amount right here is just the right amount to fill in the rest of the box. And so this is kind of my idea. I want to show this somehow with algebra to back up this geometric claim. So let's calculate these partial sums and then record them in the table. The partial sum is just like adding up only a few of these terms, like not all of them. So like the first partial sum is just going to be taking the first value, and that's going to be 1/2. The second partial sum is going to be taking the first 2 values. That's when I shaded the green and the red regions, and I think that's 5/6, right? Because I split it into 6 sections, and then there's 1, 2, 3, 4, and then 5 that were shaded in. And then for the third partial sum, that's when I kind of shaded these things in blue. There were 24 pieces, and I shaded in 23 of them. And then how about for the fourth partial sum? That's when my denominator was 120, and I shaded in all but one of them. And so that's 119 on top. So let's say I had like some kind of random partial sum, like, maybe 50 or 60 or 99, I guess. If I just have some like value, let's say k, to represent like any given step, looks like I should do k plus 1 factorial on bottom, and then 1 less than that on the top. I'm noticing like this number right here is 5 factorial, and that's 1 more than the 4, and then factorial, right? The 3 gets increased by 1 to a 4, and then I know that 4 factorial and 24 are the same thing. So that's why I'm adding 1 to that k and then doing a factorial, because that's just the pattern that I see here. So by the 99th step, I should have 100 factorial minus 1 over 100 factorial. And I think it'd actually be useful to just show like how far away from the number 1 I am. Because this sum is supposed to be 1 today. So if I do like 1 minus my partial sum, this value shows me like how close I am to the number 1. So this would be like a 1/2. This is a 1/6. This is 1/24. This is 1/120th. And so this pattern right here looks like it's just 1 over k plus 1 factorial. So that means like, say for the fourth partial sum, if I just add 1 over 5 factorial, that's this number right here, I have now reached the number 1. So for step 99, I should add 1 over 100 factorial, and that will get me to the number 1, which is weird because we're adding 1 over 101 factorial instead of this one that I came up with. I think all my math is right. Like this pattern I'm noticing with geometry, I recorded this stuff in the table. These patterns exist, I think, the way that I think it is. I might be inclined to say that the problem's actually a little bit wrong here, where either this should be a 100, right? So that we could be at step 100 over here, and then we would need the 1 over 101 factorial, and then that would line up with the problem. Or maybe the 99 is fine, but we'll actually need to change this to be the 100 factorial instead, which is the one that I found in the table right here. Huh. All right. So looks like if all my math is right, and I think it is, this problem needs to be corrected slightly. Either the upper sum has to be 100, or this has to be the number 100. And I feel like it looks a little bit neater to just cross off this 99 and then put a 100. So that would put me right here on the table where I have 100 terms in my sequence. And then therefore my partial sum will be 101 factorial minus 1 over 101 factorial. And then once I do this new value for y, and I add 1 over 101 factorial, I should get the number 1, right? Because let's just do a little bit of substitution. I'm pulling this from my table right here. And then I'm adding the 1 over 101 factorial from the problem. And then I guess if I split the denominator here on this fraction, I could show this as 101 factorial over 101 factorial minus 1 over 101 factorial. I'm kind of like distributing it almost between the two parts of my numerator. And then I can tell that these last two fractions here cancel out like that. And then anything divided by itself is just 1. Okay, well, I guess except for 0, but an obnoxiously big number divided by the same obnoxiously big number is just 1. And so with a little bit of a correction to the problem statement today, x is 1. So, all right. I am going to keep this here because I believe that that is the case, that the upper number should be 100. And once you do all the math, the sum is 1. So this is a really interesting pattern. I really did enjoy this problem, and I kind of liked how this geometry approach helped me write the sum. And I guess, yeah, I just needed a little bit of correcting for x to actually be equal to 1 today. So I'm all done. That's my solution, and I hope you enjoyed. I'll see you in the next video. Bye.